Section 5.5 is about solving trig equations. A couple of important notes. First of all, 5.4 we didn't cover. That was part of the plan. That covers some sum to product and product to sum formulas for trig. Useful, but we tend not to use them a whole lot, so they weren't part of the curriculum. Okay. 5.5, solving trig equations, probably the most important trig skill you're going to need for calculus next semester. Okay. So super, super important that you master this skill. And this is just one section of our textbook. I've set things up so that we've got time to go through this pretty thoroughly. We can spend more than a full day on this one section. Some of you are going to be fine after we do that. Okay. Some of you might say, you know, there was a lot going on there. I'd really like to see some more worked examples. Fortunately, I taught trig last semester. In our trig class, there are actually 2 sections of the book devoted to solving trig equations, and all of those videos are posted on Canvas under additional trig resources. Okay. So start with the video playlist for this semester. If you feel like you want some more worked examples, you've got those other videos right there. All right. Now, for this particular problem, I'm giving us the trig equation sine x equals negative root 3 over 2, and I'm giving us directions in 2 parts. First of all, we're going to find all solutions in 0 to 2 pi. Notice 0 is included, but 2 pi is not. So there are actually no coterminal angles in that interval, and that interval corresponds to 1 period of pi, which happens to correspond to 1 rotation around the unit circle. And then part B, we're asked to find all solutions. Now, sometimes you got to make sure you read the directions. Sometimes you'll be given both parts. Sometimes you'll just be asked to find the solutions in a particular interval. Do that and you're done. Sometimes you might just be asked to find all solutions. If so, even if you're just asked to find all solutions, I'm still always going to start by finding all of the solutions in 1 period of the function and then finding all of the solutions. Okay, now with this particular problem, it's kind of nice. This is a linear trig function, and all that means is that the biggest power of a trig function that we have is the first one. So we're not dealing with any trig functions squared or taken to higher powers. And this is in the form that I want. I've isolated the trig function, so a trig function equals a number. If I can get it into that form, I'm in good shape. Now, that number you might recognize. For those of you who are more circle people, you might say, oh, I know the points on the unit circle where the capital Y value is negative root 3 over 2, and so you can just go right to the answer, and that's fine. I'm going to show you how I work it out because I'm more of a triangle person. And even if you already know the answers to part A from just having memorized the unit circle, do pay attention, because there are going to be some times where we don't have a value that we've memorized on the unit circle, and so we do have to think through the process a little bit more. So the first thing I like to do is think in terms of quadrants. Okay. Most of the time, I'm going to have 2 solutions in 1 period of sine, 1 rotation around the unit circle, because there are 2 quadrants in which sine is negative. So, will I have a solution in quadrant 1? No, because sine is positive there. 2? No, because sine is positive there. But I will have a solution in quadrant 3, and I'll also have a solution in quadrant 4. I'm actually going to draw 2 separate pictures. So I'm going to have an angle x that lands in quadrant 3, and I'm going to have an angle x that lands in quadrant 4. And if I'm looking between 0 and 2 pi, I want to make sure that I'm rotating counterclockwise less than 1 full revolution in order to get to that location. Okay. So there I took into account the fact that my sine value was negative. Now I'm going to think in terms of the reference angle. I like to just call it alpha. Okay. And what I know is that sine of alpha would be the absolute value of negative root 3 over 2. Because remember, when I'm evaluating trig functions, I use the quadrant to figure out whether it's positive or negative, and then I use the reference angle to calculate the absolute value that I attach to the plus or minus sign. Here we're just doing that backwards. We're using the plus or minus sign to figure out what quadrant or quadrants we're in. Okay. And then we're going to figure out what the reference angle is by saying that its sign will be the absolute value of this, which is just root 3 over 2. Now, the reference angle is always an acute angle, okay? By definition, it's always a positive acute angle, and that's somewhat redundant because acute angles are positive, okay? So, if its sine is root 3 over 2, now I might have that memorized. I might just very quickly draw my 30, 60, 90 triangle and say which of these angles has a sine of root 3 over 2. Looks like it would be 60 degrees. I'm working in radians though. Notice this told you, without my having to explicitly say it, that we were working in radians. So 60 degrees in radians would be pi over 3. And it's the same reference angle for both pictures. In this picture, x would be pi plus pi over 3, because I've rotated a little bit past pi. Notice that's just 3 pi over 3 plus pi over 3. So that would be 4 pi over 3. In this picture, we're this much shy of a full revolution. So it would now here be 2 pi minus pi over 3. So x is 2 pi minus pi over 3. That would be 6 pi over 3 minus pi over 3, or 5 pi over 3. So my answer to part A is 4 pi over 3 and 5 pi over 3. Those are the two angles, one in quadrant 3, one in quadrant 4, in this interval that have a sine of negative root 3 over 2. Okay, to find all solutions, I'm just taking advantage of the fact that all my trig functions are periodic. So, if at this angle I'm at a sine of negative root 3 over 2, if I add a multiple of the period, I'm going to be at another place where sine is negative root 3 over 2. Because the period of sine is 2 pi, adding a multiple of a period actually just takes me to a coterminal angle. It would bring me to a different angle, but that would have this same terminal ray and therefore would intersect the unit circle 2 times. So I can say it's 4 pi over 3 plus 2 pi times n. Now I'm letting n here represent an arbitrary integer. Okay. So if n happens to be 0, because 0 is an integer, then I'm just getting 4 pi over 3. If n is 1, I'm coming 4 pi over 3 and then adding a revolution to that, and so I'm going to have a coterminal angle. And integers can be negative, so if n is a negative angle, that just means that I'm coming 4 pi over 3, but then I'm rotating the other way, so I'm subtracting a multiple of 2 pi, and that works as well. Okay, so I'm going to have this. I'm also going to have 5 pi over 3 plus 2 pi n. But anytime I introduce like this a variable, like this n here, if that's not taking on just any old real value, it's restricted to taking on integer values, I need to say that. I don't here want n to be a half, because if I added half of 2 pi to this angle, it would put me in quadrant 1, I wouldn't have a solution. So I need to make sure that n is an integer. So I can either write n is an integer, but we're going to be solving an awful lot of these. And writing that out starts to get kind of tedious. So there is a shorthand for doing that. You folks are familiar with this symbol. This symbol just means the set of all real numbers. Well, in a similar way, a z with that same sort of script to it means the set of all integers. So if I don't feel like writing out in words that n is an integer, I can just write n. This e-looking symbol means is an element of, or is in the set of, and then I can put this symbol for the set of all integers. Okay. But anytime you're finding all solutions, you will need to introduce a variable that's representing an arbitrary integer, so you'll either need to write out n as an integer, or n is an element of the set of integers, as I've done here.